Bismillahirrahmanirrahim. Assalamu alaikum, dear friends. We are now starting the second lecture for week number 3 for our course of systems. If you recall, in our last lecture, we talked about the system representation in time domain and frequency domain. In communication systems, generally, we have many subsystems or blocks actually. If you recall, when we were having introductory discussion regarding communication systems, I divided communication systems into three major blocks. One was transmitter, another was channel, and third was receiver. In fact, transmitter and receiver, they are actually composed of many further sub-blocks. So generally all types of communication systems, they are representative of many interconnected building blocks or subsystems. In order to represent the relationship between different blocks and different subsystems, a common representation is to use a block diagram. So a block diagram is actually representative of how different components are interconnected with each other. Recall that in our last lecture we described a system as a two-port block where you have an input port and an output port, and system system transforms the input signal into the output signal. This two-port block can be connected in variety of different fashions. The interconnections that are commonly used in communication systems are these three. One is called cascaded connection, second one is called parallel connection, and third is called feedback connection. And by multiple types of connections, we can have different types of implementation of different systems. Let me illustrate these three different connections. This is the first one is the parallel connection. Here you can see that there are two subsystems. One is represented by transfer function h1f and the second one is represented by transfer function h2 of f. Note that I have represented this system in frequency domain. Generally we used to represent blocks in frequency domain, but they can also be represented in time domain as well. So the expressions that we are representing here, they are actually frequency domain expressions. You need to make appropriate changes whenever you make a block in time domain. For example, you can see that here these two are in sum form. In time domain also the sum remains sum, so they can be represented exactly in same way if you are making the block diagram in time domain. However, for this case you can see that these two are actually multiplied, and the frequency domain multiplication is actually time domain convolution. So if you try to plot this type of block in time domain, so it will be represented by convolution, not the multiplication. So this is a word of caution for you that the representation that I am discussing here is actually frequency domain representation, and although we will be using this representation more often, but if you need to use a time domain representation, so you need to make appropriate changes. Okay, so we were trying to discuss different types of connections that are used as building blocks, building a complex network. So first one is the parallel connection, where you can see that the output is actually sum of two different subsystems, is illustrated here. So if you have an input which is represented as xf, the signal goes through one subsystem which is h1f, output will be h1f into xf. Similarly, the same input also goes through another subsystem which is h2f, and the output will be h2f into xf, and the overall result of this parallel combination is actually sum of these two individual outputs. So the output yf is actually sum of H1F plus H2F xf. So you can say that the equivalent result of these two blocks is actually sum of their frequency response. So if I replace them with a block having the response which is equal to H1 plus H2, so both of them will be behaving exactly the same. The second connection is called cascaded connection. In cascaded connection, the output of one network is actually input to other. So you can see that the first subsystem is represented by H1F. Whatever output you are getting from the subsystem is actually fed into the second subsystem, which is represented by H2F. This is the same combination that we used to illustrate the basic block diagram of communication system, where we placed transmitter, channel and receiver in a cascaded fashion. So in this case, if you have two or more cascaded systems, the overall response will be equal to the product of individual frequency responses. You can calculate this result directly from this expression. You can see that if you have an input which is applied to the subsystem with frequency response of H1F, the output will be H1F multiplied by XF, and if this output becomes input to the second subsystem, which is represented by the frequency response of H2F, in that case the overall response will be multiplied by this H2F as well. So you will get the overall response to be equal to H1F H2F into XF. So in other words, the equivalent effect of two cascaded block is equal to the product of individual frequency responses. The third combination is named as feedback connection, where the output is actually fed back to the input system. So this is the block diagram related to the feedback connection. You can see that the input XF is applied to the system H1F. Whatever output you are getting is fed back to the input. You can see that is illustrated with a minus sign here, which is named as negative feedback. So we have a negative feedback which is shown here, and if you simplify, you can calculate that YF would be equal to H1F upon 1 plus H1F H2F to XF. So this is the overall effect of this this feedback connection. So equivalent block should have this transfer function. So these are three commonly used connections that we use to represent a block diagram, and by using these connections we can represent and evaluate different types of complex interconnected systems. So with this we conclude the discussion related to systems. Now I want to explain an important unit that is very commonly used in communication system, and that unit is decibels. But before describing this decibel, let me quickly define gain and attenuation, which are commonly used in communication systems. We know that the system is actually comprises of different subsystems, and all the circuits, they have certain properties and they manipulate the signal in some way or other. So one of the important effect of all types of system is their attenuation. When signal goes through that system, there is some power loss in the system, which their power loss is called attenuation. Another important thing is gain. Typically all the communication systems, they have amplifiers at the transmitter as well as the receiver sides. These amplifiers, they are used to increase the value of output signal or provide some sort of amplification. So the factor by which this amplification is provided is named as gain. So we define gain mathematically as the ratio of the output voltage to the input voltage. So if you have an amplifier which provides certain amplification to the voltage signal, so that will be represented by this thing. So this amplifier should have certain gain, which I have illustrated by A. So this A can be directly calculated by dividing these two. As we are focusing on voltages, so typically this gain is named as voltage gain. However, in most cases we are interested in calculating power gain. Power gain is also defined in the same way as we define for the voltage, but the parameter that we use to calculate that gain is power, not the voltage. So power gain is actually the ratio of output power to the input power. So I have shown this power gain to be represented power gain with subscript P in order to show that this is the power. So the power gain is defined as output power divided by input power. So let us take a very simple example. Say for example, if we have a power output of an amplifier which is 6 watts, so we know the output power, and the gain is given as 80. You must know that this gain does not have any specific unit, because this is the ratio of two same quantities, out and in they are both in watts, so gain would be a dimensionless quantity. So what is the input power? So we can calculate input power directly from the definition of the gain. AP is this power gain is actually ratio of output power to the input power, and from here we can calculate input power to be equal to output power divided by gain. So if we substitute the values, we can simply get out input power to be equal to 0.075, or we can write it as 75 milliwatts. Similarly, as we discussed previously, that sometimes we use multiple systems in cascade or in other connection. We can sometimes use amplifiers in cascade as well. In communication systems also, we typically use amplifiers in 2 or 3 stages. So amplification is generally performed in 2-3 stages. So each stage has certain amplification. So in that case, each amplifier is considered to be in cascade. So overall gain would be equal to the product of individual circuit gains, because we are working on number of cascaded amplifiers. So if you have more than one amplifier, so you can use their individual gains to calculate the overall gain by simple multiplication operation. So for example, I give you a simple case where we have 3 cascaded amplifiers, and each of them has a power gain of 5, 2 and 17. So these 3 has gains like this: 5, 2 and 17. So because we have a kind of 3-stage amplification, so we would be getting a total overall amplification in the signal. So what would be that overall amplification? That is equal to the product of these individual applications which are provided at individual stages. So the overall power gain would be equal to the product of individual gains, which I have illustrated as A1, A2 and A3, and if you multiply them together, we will get an overall power gain to be equal to 170. So this cascaded connection has a gain of 170, and now we are given the input power, which is 40 milliwatt. So what should be the output power in this case? So you can calculate the output power by using the gain formula, which is defined as output power to the ratio of output power to the input power, and from here you can find out that the output power is actually gain multiplied by the input power. So it comes out to be 6.8 watt. Okay, defining gain in a ratio manner would also enable us to define attenuation in the same fashion. Actually, attenuation is referred to a reverse condition of the gain. as I mentioned that gain relates to the increase in power by amplification phenomena. Similarly, attenuation refers to the loss of power. So all the circuit components that typically contribute to some sort of attenuation. So there is overall loss generated by the circuit, and that loss is named as attenuation. So in attenuation, the output signal would be lower in amplitude than the input signal. So overall circuit would be a lossy circuit or attenuator where the output signal would have smaller amount of power. So in order to maintain uniformity with the gain, we define attenuation as reciprocal of the gain. You can see that I have defined it as ratio of input to the output. So it can be defined as V in upon V out. In other words, attenuation or gain, they are actually two views of same thing. If a gain is greater than 1, in that case it's actually referring to some sort of attenuation amplification. But wherever we get a gain which is less than 1, in that case that gain which is less than 1 is actually referred to attenuation, because in that case the output power would be smaller than the input power. So attenuation can also be taken as gain which is less than 1. And similar to the case of amplifiers that we discussed in previous slide, different attenuators, when they are cascaded, the total attenuation would be equal to the product of individual attenuations. So say for example, we have a simple block diagram illustrated here. So we have different attenuators which are available here. You can see that this is this overall system comprises of 3 subsystems where each subsystem has certain sort of loss or attenuation, but I have represented them as A as gain which is less than 1. So A gain equal to 0.2 refers to some attenuation. Similarly, this loss circuit 2 has gain which is 0.9, which is less than 1. So this is again referring to some sort of attenuation. Similarly for the case stage 3. So if I ask you to calculate the total attenuation, so it would come out to be 0.018 by simply multiplying the individual factor for each stage, and the output voltage will be equal to this overall gain multiplied by the input voltage. So this comes out to be 32.4 millivolt, which is actually smaller than this input voltage because of the attenuation in the system. In communication systems, a common technique is to represent gain and attenuation in a special unit which is called decibel. Remember that I mentioned that voltage gain and power gain, they are actually dimensionless quantities. So they do not have any unit, but the decibel unit is actually referred to a logarithmic version of that ratio. So we always calculate this decibel in form of a ratio. You can see that we have a ratio here and represent them as a decibel unit. So a common this decibel unit is a common unit whenever we try to calculate the overall gain or loss in the circuit. So good thing in this decibel unit is that we use logarithm to define this unit, and the property of logarithm is known to us that whenever different quantities are multiplied in logarithm, so they become addition in individual logs. So if we convert the unit into decibels, so gain and loss, they become in form of addition rather than multiplication. Recall that in previous slide the total gain was represented as product of individual gain, but if the unit of decibel was used in this scenario, so we should have added them together rather than multiplying because of the use of this logarithm. So how do we define this decibel unit? So decibel unit is defined for voltage, current and power like this. So if we have a ratio, voltage ratio V out upon V in, we take a log and multiply by 20. So this is called the voltage gain in decibels. Similarly, the current gain in decibels is defined the same way. However, you should note that the power gain in decibel is defined with a constant factor of 10 at the beginning. So this different definition for power gain is actually used commonly because of consistency with the other notation. We know that the power is actually related to the voltage squared. So this square is appearing here. You can see that the power becomes multiplication in logarithm. So if you multiply 10 by this 2, so if you represent the same thing with voltage, so this becomes 20. So defining power gain separately makes a consistent notation of use of notation in terms of voltage and power. So that's why we define them in this fashion, that voltage and power gain in decibels, they have a multiple of 20, and power gain of the power gain has a multiple factor which is 10. So let us take a simple scenario where we have an amplifier that has an input of 3 millivolt and the output is given as 5 volt, and we intend to calculate the gain in dBs, and you can see that these quantities, they are given in volts. So we should calculate the voltage gain formula, which is illustrated here. V out upon V in, log of V out upon V in multiplied by 20. So if we use this formula, V out, the output voltage is given as 5 and the input voltage is given as 3 millivolt, which is 0.03. So if we simplify this thing, you would see that the dB value of this gain comes out to be 64.4. There is another example here. Now we have a filter that has a power input of 50 milliwatt and an output of 2 milliwatt. So we know the input and we know the output, which is 2 milliwatt. So what is the gain in this case? You can see that these are in watts, that means these are the power ratios. So we should use the formula of the power gain, which is illustrated here, 10 log P out upon P in. So if you use this formula, the dB value of the gain should be equal to 10 log of the output voltage is 2 milliwatt and the input gain is 50 milliwatt. You can see that I have ignored the milliwatt in numerator and denominator because this is a common unit in both sides. Even if you include the factor of 10 raised to power minus 3 in denominator and numerator, it would cancel out. So you can include or do not include, it doesn't matter here. So if you simplify this thing, you would get a value of minus 13.98. This minus 13.98 of gain is actually referred to attenuation. Generally in decibel values, the positive values, they result whenever there is an amplification, and negative value results whenever there is an attenuation. So you can see that when we use the gain formula in decibel, we get a negative value. So this is actually the attenuation. Alternatively, we can say that this system has a 13.98 dB of attenuation. So if you write it gain, so it will be written as minus 13.98 dB. If you write it attenuation, so it will be written as 13.98 dB attenuation. Okay, so this is the decibel unit that we have used. One important thing that you should notice that the decibel unit is defined for ratios V out upon V in. Sometimes we do not have a specific ratio. Say for example, if I ask you to convert this 50 milliwatt into decibels, we cannot convert it unless it is divided by some value. So if we need to convert a power with certain value in decibels, so generally we use a reference point and calculate the ratio here. The commonly used reference values are 1 watt or 1 milliwatt. So if you are given some power and you want to convert it into decibels, so what we do, we divide it by 1 watt and calculate the gain. So you can see that this 10 log P upon 1 watt is actually the dB value of this power. So because we have used a reference of 1 watt, the denominator is 1 watt, so this is generally named as dBW. So this is another form of dB unit which is named as dBW, where you have used 1 watt as a reference. Similarly, sometimes we use a reference to be equal to 1 milliwatt. So whatever power is given to you, we simply divide it by 1 milliwatt and convert it into decibels. So because we have used a reference of 1 milliwatt, so we name it as dBm. So dBm refers to the dB value with reference to 1 milliwatt power. So the division factor that we have used is actually 1 milliwatt. And there is a common relationship between this dBm and dB value. Whatever power you would get in dBm, that will be equal to the power in dBW plus 30 dBs. The last thing that I want to mention is that because of the use of logarithmic unit, the multiplication would be transformed into the attenuation. So if you recall, let me go back here. The gain was defined like this. So P out, output power, is actually the gain multiplied by input power. This expression is actually not in dB, so this is a fractional expression. If we try to write the same expression in decibels, so this multiplication would get transformed into addition. So if you are solving the system in decibels, so output power would be written as this gain in decibels plus whatever power input power you have in decibels. So this, in order to conclude our discussion, let me take another example. We have discussed so far that we can have a system which comprises of many subsystems, and typically in communication systems we encounter a cascaded connection where there are multiple components, where one output of one component is fed to the input of the other component, and so on. And each individual component, they can have certain gain or attenuation. So in overall version, you would be having an overall gain or attenuation in the system. In order to illustrate this overall scenario, let me take a simple example here. So let us have a system which is comprising of 4 stages. You can see that it's a cable section here, an amplifier, another cable section, and an output amplifier. So an input power is shown at the input side, and there is an overall output power. So let the input power to the repeater system shown in figure is P in is equal to 0.5 watt. So we know this P in power, which is 0.5 watt. The cable generally is attributed with certain certain loss. The loss in any cable section is actually related to the length of the cable. The shorter length gives a smaller amount of loss, and the longer length would give a higher loss. So typically the cable losses, they are illustrated in terms of an attenuation coefficient, which is actually the loss on per kilometer basis. So this cable section has a loss of 2 dB per kilometer. So if you have a 1 kilometer length of cable, in that case there will be a loss of 2 decibels. We are given that the total path length of the system is 50 kilometers. So from this stage to this end we have a total length of 50 kilometers. So what do we need to find here? So we want to find the amplifier gains. So we need to find this G2 and G4, these two gains which are used in this system, and the location of the repeater. So where should we locate this repeater? Here, this repeater. So because the total length is 50 kilometers, so after a certain distance it should be placed. And what is the requirement in the system is that we want to have an output power of 50 milliwatt. First thing, the output power should be 50 milliwatt, and the power input to each of the amplifier is 20 milliwatt. So we want to have power at the input side of each amplifier to be equal to 20 milliwatt. So this is our problem. We are encountered with a 4-stage system with certain gains and losses, because amplifiers would be providing gains, whereas the cable section would be providing some loss. And we want to calculate 3 things. First is the location of this repeater, second is the gain of these two amplifiers. So let us start our problem. As I mentioned, in most cases it is convenient to calculate the gains and losses in decibels. So first we transform the given values in decibel form. So input power is given as 0.5 watt, so we would transform it into decibels. As I mentioned, in order to transform this 0.5 watt into decibels, we need to use a reference point, and that reference could either be 1 watt or 1 milliwatt. So for this purposes we have chosen 1 milliwatt here, although it would not make any difference if you have chosen 1 watt. So the same calculation can be done if you have taken 1 watt as a reference. So if we transform this Pin into dBm, in that case this will become 27 dBm by simply dividing this thing by 1 milliwatt, taking log and multiplying by 10. Similarly, the output power is given as 50 milliwatt. If you transform this in dBm, it will give the value of 17 dBm. The required power at the amplifiers is 20 milliwatt. Again, we need to calculate it in dBm. So I have divided it by 1 milliwatt and then took log and multiply by 10 in order. Overall result comes out to be minus 17 dBm. So first we have transformed all the powers given in the question in dBm. Now let us first try to calculate the position of this repeater. So let me assume that this repeater is placed at a distance d from the start of this system. So let's say we have replace this repeater at a distance d, and of course all distances are taken in kilometers, so I am assuming that this d is also in kilometers. Now come back to this problem. If you see that what the power which is input to this amplifier is actually PA, the required power which is input to the repeater is 20 microwatt. This is given to us. We know the input power, and there is a cable section in between which has certain loss. So you can see that if this power was input to the system, after getting this loss L1, we get the power of PA at the receiver. So this PA power would be the input power minus loss. Of course loss will be subtracted with the system because it refers to the decrease in the power. So this PA, so this gives you that PA should be equal to Pin minus this loss, because cable section is of d kilometers long, and each kilometer has an attenuation of 2 dB per kilometer, so it should be replaced by alpha d, so that you calculate the overall attenuation. And from this equation, if you simplify this, you can easily calculate the distance where you have placed the repeater, and this distance comes out to be 22 kilometers. Okay, so now let us focus on the next section here. Let's say we start from this repeater to the input side of other amplifier, and we know that the other amplifier also requires the input power to be equal to this 20 microwatt power, which is represented as PA. So from this to this, you can see that there is one gain, which is this amplifier gain, and one loss, which is this cable section loss. So this PA power would get some gain, which is G2, and it will get a loss, which is L3. So this overall PA, the output PA power at the output amplifier would be equal to the power at the input side of this section, which is also PA in this case, plus there was a gain of G2, and minus there is a loss of L3. And you can see that as we know that the overall length is 50 kilometers. So this, because this section is of d kilometer long, the other section would be 50 minus d kilometer long, because the overall length is 50, so this will be 50 minus d. So the length of the cable is actually 50 minus d in the second section. Therefore the total loss will be alpha into 50 minus d. And if you simply substitute all the values here, you would get the gain of the second amplifier, which comes out to be 56 dB. So the repeater amplifier, which is placed at 22 kilometers from the transmitter, it should have a gain of 56 dBs in order to maintain the required amount of power at the output side. Now let us move on to the last part, which is this section, the output section. The power at the amplifier is represented as PA, the output power is Pout, and they are directly related with the gain. Simple. So PA would get a gain and would give you an output power. So if you look at this expression, so this output power would be equal to this PA, which is the amplifier power, plus the gain of the amplifier, which is represented as G4. And if you simplify this thing, the required output power is 17 dBm, and the gain, the amplifier power is minus 17 dBm. And from this relationship, you would see that the gain comes out to be 34 dB. So the gain of the last amplifier would be 34 dB. So you can see that we have calculated the location of the first repeater amplifier. It should be placed at 22 kilometers, and we have also calculated the gains of both the amplifiers. The first one, the repeater amplifier, should have a gain of 56 dB, and the output amplifier should have a gain of 34 dB. Note that the gain is always mentioned in dB, not in dBW or dBm. So this is how we can calculate the power which is present at different stages in an overall network, where we have to treat different sections individually, and by relating the power at the input side and output side of the individual subsection, you can easily calculate the individual missing parameters which are required for that particular type of analysis. So we would conclude the discussion here. Thank you all.